We will now discuss about consecutive reactions. As the name suggests, consecutive reactions means a reaction takes place in a consecutive fashion. So A gives rise to B, which is known as an intermediate, and then the intermediate B gives rise to the product C. And let us define some rate constants K1 and K2. In this case, this is consecutive irreversible reaction. Now, solving this equation, for A is pretty straightforward because A to B is just first order. So, you can always solve it right away. A is A0 e to the power minus K1t. Now, solving the differential equation for B is little bit tricky because B is being formed from A and then it is being consumed to C. So, that needs a particular integration, and you can always go to the YouTube lectures to see how this is solved. So, I am writing the answer here. So, if you solve this rate law for B, you will get the rate constant or the rate law something like K1 by K2 minus K1 into A0 times e to the power minus K1t minus e to the power minus K2t. Similarly, you can also get a equation for C which will be something like A0 times it will be 1 minus K1 by K2 minus K1 e to the power minus K1t plus K2 divided by K2 minus K1 e to the power minus K2t. So, these are the solved solution of the differential equation. These are the integrated rate laws. Now, using these equations, we can now plot the concentrations of A, B and C with respect to time. Now, it will depend in this case what are the relative magnitudes of K1 and K2. Now, let us first assume that K1 is much greater than K2. In this case, what will happen? The concentration of A will fall readily with a rate constant which is e to the power minus K1t, which a rate. So, in this y-axis I am plotting the concentration of A or B or C, and I am plotting it against time. So, this curve is for A. Now, for B, if you look at the equation for B, it is actually has two terms, e to the power minus K1t and e to the power minus K2t, and in this case K1 is much greater than K2. So, you can approximate also this prefactor to be equal to nearly 1 because it will be K1 divided by K2 minus K1. So, it will be close to minus 1. So, then you can make some approximations. You can actually look at the video for this earlier course where the details were discussed, and then you can show that the plot of the B will be something like this. So, the initial concentration of B first rises and then falls, and then C grows at a very slow rate, and eventually the curve of C will be something like this. So, you can qualitatively describe what is the nature of the curve. So, as you see that the reaction goes via this, A is going to B and then going to C. Since K1 is much faster than K2, what will happen is that first the curve for A, the A will actually decompose into B very quickly because it is actually forming B at a much higher rate than B is forming C. So, the appearance of C happens much later time, and in between what will happen if A forms or A is converted into B, and as B is formed it is also converting to C but at a much lower rate. So, we will have an accumulation of B in the reaction mixture, and this is what is happening. So, at this time you can see the B actually reaches its maximum concentration, and then since it is also forming C, eventually it will form C and it will again become 0, and then the C curve slowly grows. The interesting thing happens when the opposite situation is there, whether actually the second rate constant K2 is much higher than K1. Now in that case, the curve for A will be much slower, because A now is decaying at a rate which is e to the power minus K1t, and K1 is much smaller than K2. Now for B, this is a very interesting situation, because B is forming from A at a rate which is K1, which is small, and it is decomposing first. So what will happen initially, the B will start forming at a much slower rate, which is e to the power, it's a growth actually, and it goes as with the rate constant K1, which is small. But then as soon as it forms and it has some significant little amount of concentration, it will actually keep on forming C. So as soon as it is formed, it is decaying. So what it will mean is that this initial concentration of B will be more or less kept constant over a long time, because some amount of B was formed initially, that's that over a certain time, which is known as the induction period, and then once that little amount B was formed, it is rapidly now forming C, because K2 has a much higher value than K1. And what will happen initially, C formation will be slow because there is no B, but as soon as B forms, C also forms rapidly, and C will form up like this. So this period is called the induction period, when the formation of the intermediate is being formed. And then over this entire period of time, as you can see, the concentration of B, of course it decreases, but it decreases rather slowly. So we can say that practically the concentration of the intermediate does not change over time, or we can say that this concentration has reached a steady state concentration. Now by steady state we mean the concentration is not changing with time. Now this steady state condition is extremely important when we discuss the mechanism of a chemical reaction. We will see in a short while how it is important. So to summarize, consecutive reactions can be solved. The equation of the consecutive reactions, differential equation, can be analytically solved, and then after you get all these solutions, you can actually try to plot them under two different conditions. One is for a condition when the first rate constant, which is formation of the intermediate, is much faster than the decomposition of the intermediate. Under that condition, you will see an accumulation of the intermediate, because it is forming at a much faster rate than it is being decomposed. On the other hand, if the opposite thing happens, that the intermediate decomposes very quickly, so then you have a steady state condition after the induction period. And this kind of steady state condition is extremely important. For example, in many cases, like when you see say for example in an enzyme catalysis reaction, when the enzyme works on a substrate, forms an enzyme substrate concentration, and then actually we can say that a steady state has reached after the induction period. And this has been well studied for practical examples will be, say, growth of bacteria in a culture medium, so that also follows after a certain induction period. Then suppose not only the growth of bacteria, particularly the enzyme degradation, or an intermediate is involved. In those cases, we'll see this kind of interesting kinetic behavior of the intermediate. Now we'll talk more about this steady state approximation, but we'll see it in a very different way. Now all these examples which we gave, like irreversible reactions, or say competitive reactions, A is going to two different products, it can be reversible also, and then finally to these consecutive reactions. So these reactions, the way we dealt with them is kind of elementary reactions, because we said that these are three basic elementary reactions. which will be using mostly the consecutive type and the reversible type reactions, which will be using frequently to explain the overall rate law for a composite reaction, which is actually composed of many elementary reactions. So let us first give you an example of how one should proceed this problem, which is known as the mechanism of a chemical reaction, mechanism of a composite chemical reaction. So the entire idea is that any composite reaction can be decomposed into a bunch of elementary reactions. So almost all chemical reactions, the way we see it in a laboratory, are actually composite reactions. Now, to understand the mechanism, we have basically two hypotheses or two approximations which are frequently used. The first one is known as rate determining equilibrium approximation. Where we approximate that there is a pre-equilibrium which exists between the reactants. Let's say I have some reactant which is A plus B, which is forming a product or an intermediate. Let's say I call it as I, and then this I eventually gives you the products, which I denote as P. So what I am saying here, the overall reaction, let's say, is something like A plus B is going to product, and there is some rate constant which is the observed rate constant. That's why I am writing it as suffix OBS, which is the observed, experimentally observed rate constant, and I am assuming the reaction actually happens via a pre-equilibrium followed by a step, and this step is nothing but the rate determining step. So this step dictates the overall kinetics of the reaction, because this step is slow in nature, and we are assuming that this step is fast in nature, in the sense that there is a first pre-equilibrium, in the sense as soon as I is formed, I also gives you back the product. So under that condition, this equilibrium you can think as if it is a separate equilibrium, although you cannot truly, because the I, the intermediate, is not only a part of the equilibrium, it is also part of the second step. So we have basically two steps here. So the second step actually is forming the product, but since it is a slow step that we have approximated, we can think that this equilibrium is kind of isolated. Now from this equilibrium, I can easily write that the concentration of I divided by concentration A and B is nothing but the equilibrium constant, which is the ratio of the forward and the reverse rate constant. So we can readily say what is the rate of the reaction. The rate of the reaction for a multi-step reaction will depend on the slowest step, because the slowest step creates as if it is a bottleneck to the reaction. Now this rate determining step approximation, it's not an approximation, I mean it is the valid thing, where you say that if a reaction is composed of many different steps, the overall reaction or the rate of the overall reaction is actually controlled by the rate of the slowest step. Now this is realized in many day-to-day phenomena. For example, if you have a highway and there are some different lanes and cars are going through the lanes at different speeds, you will see the overall speed is actually dependent on the speed of that lane where actually the cars are moving with the slowest speed. Again, another example will be if you have a toll tax or something like that, toll plaza, and then the velocity of the cars are slowed down because you have to wait, pay the tax and then go, and then the overall speed is dependent how frequently the tax is being collected and the cars are being late to go. So this is the very general concept of kinetics. In that case, I can write the overall rate of the reaction is rate of the product formation, which is in this case the dP dt. Since these are all elementary steps, I can directly write it as this is from the stoichiometry. I'm writing it using the stoichiometry of the second equation because it is an elementary reaction. So it is K2 into the intermediate concentration, and then the intermediate concentration I can easily get from the equilibrium, and which will be nothing but K2 times K1 by K minus 1 into A into B. Now you see that the observed rate law is nothing but a combination of K2, K1 and K minus 1. Now we could actually explain this mechanism in a very different way, there we'll just use this concept which we just discussed, which is the steady state approximation. Here we considered the same thing, the same kinetic equation, like A and B initially forms a product, and the product, an intermediate, and this intermediate also gives back to A and B. But here the approximation is slightly different. What we're going to say is that this intermediate is under steady state, so that the concentration of the intermediate doesn't change with time. That we are going to approximate here. And then in the second step, as before, so this is the first step and this is the second step, and in the second step I will have a direct formation of the product with a rate constant K2. Now what is happening here is, let us find out what are the terms that involves this di dt. So if I see the first step, the product I is being formed at a rate constant with a rate constant K1. So it's a bimolecular reaction. These are all elementary reactions. That's why from stoichiometry I'm directly writing it, and it is also being decomposed with a rate which is K minus 1, and then it is also decomposing in the second step into the product. So if I collect the terms, I can easily see that the intermediate concentration is nothing but, if I take this as common, it will be minus K minus 1 plus K2 into I. So if I take the I on the other side, because this entire thing is 0, and then I will be nothing but K1 and into A into B and divided by K minus 1 plus K2. And then the rate of product formation as before is nothing but K2 into I, which is nothing but K2 into K1 divided by K minus 1 plus K2 into A into B. Now you see that the rate laws which we derived using the equilibrium approximation and the second approximation, which we already told as steady state approximation, are slightly different. You see here that in the final rate law I have K observed is K2 K1 by K minus 1, whereas in the steady state approximation I have an extra K2 here. So if we assume that this K2 is much smaller than K minus 1, then again it reduces to our earlier rate law which we got from equilibrium approximation. Now we'll see what is the connection. What does it mean that K2 is much smaller than K minus 1? Now if you think in a deeper way, so let us just multiply both sides by intermediate concentration, which is basically K2 into I is much smaller than K minus 1 into I. So what it means is that the rate or the velocity of the process 2 is much smaller or much slower than the velocity of this reverse reaction. Now if you remember our original steady state approximation, the way we arrived at in the case of consecutive reaction, where we have A is going to B, B is in this case in our new notation the B is nothing but that intermediate, and that intermediate is forming C. The steady state is achieved when the intermediate is rapidly removed. Here we are saying that okay, fine, we can actually rapidly remove the B from the mixture, but it need not be the K2 has to be higher than K1. It can be the reverse reaction K minus 1 can also be higher than K2. So somehow you have to remove the intermediate from the reaction mixture as soon as it is formed. Either it is giving product or it is giving back to the reactant. In this case, the approximation says that if I think in the other way, that it is giving me back the reactant, then also I call it as a steady state, and then I see the equilibrium approximation and the rate determining approximation both actually give the same expression for the observed rate law, which is a composite rate constant, observed rate constant. Now, thus we see how one can actually use these two approximations which are frequently used. One is known as equilibrium approximation, where we say that equilibrium or a pre-equilibrium exists between the reactants and the intermediate, which can be isolated from the rest of the equations where or the reactions where the intermediate is eventually forming the product, because it's a fast equilibrium. And the other approximation, we said that there is no such equilibrium, but what is happening due to the fine balance between the different rate constant, the intermediate's concentration doesn't change, or the intermediate concentration has reached a steady state. And we see the connection is that the reverse reaction, which is the K, which has the rate constant K minus 1, if I make that very fast, that also gives me the same steady state approximation. So there is a slight, it's often students do not get this thing very correctly or understand it very correctly, that when we talk about the consecutive reaction, we say that it is a irreversible consecutive reaction. A is going to B, B is going to C. And then when you do the approximations, instead of the first step being irreversible, we write it as a reversible. So A is going to B, B is going back to A, and then B is also giving me the C, which is the product. Then we say that just like in the irreversible consecutive reaction, the removal of B or the intermediate has to be fast than the formation. In this case, instead of K2 being higher, we can actually make K minus 1 to be higher than the K2. Now you see here, if I make that condition that K2 is much smaller than K minus 1, which means K2 is actually small, which means again that the second step, K2 is the rate constant for the second step, it's much smaller, which again tells you that that is actually the rate determining step, which is the earlier approximation. So that is the connection between the equilibrium approximation or rate determining step approximation and the steady state approximation. And the connection is that when you make this condition that the back reaction in the first step is much faster than any other step, then only you can show that these two approximations are the same approximations. And then using this approximation, we can actually explain many other things and many other composite reactions, so which are usually covered under the mechanism of chemical reactions. And usually in textbook you will get a great variety of this mechanism of the chemical reaction. For example, we gave you an example of this reaction, H2 plus Br2 is giving 2 HBr, and the rate of the reaction, which we can express as in terms of say product, which is dHBr dt, was found to be extremely complicated. And if you remember, it was something like 1 rate constant times H2 into Br2 and then divided by 1 plus another rate constant, and then we had the HBr, the product concentration, divided by Br2. Now this reaction is thought to be composed of many steps. First, actually this bromine atom gets collides with some another atom of bromine or hydrogen or the wall of the container to give bromine radicals, and then this bromine radical actually initiates the chain of reaction. So these things are called chain reactions, and we can actually divide this entire equation by many such steps. Each of these steps are actually elementary reaction. So what we do ultimately is that we find out what are the intermediates, and in this case the intermediates are radical intermediates, which are bromine and iodine. And what we do is that we apply the steady state condition for each of these intermediates, which is for the bromine and the iodine, bromine and the hydrogen atom, and we make under steady state condition we say that this will be 0, and we figure out from all these equations what are the kinetic equations, and from that we figure out what is the concentration of H and what is the concentration of bromine. Then we find out the rate law, which is half dH per dt, and we write it as a function of hydrogen radical and bromine radical concentration, and from these values we just incorporate it here to find what is the final expression. And if you work out through all this mathematics, you will figure out that you will get back to this equation after certain approximation. So this is done, or this is given, this particular example as a problem in many textbooks, but we derived it in the earlier lecture, which will get it on YouTube. Now also as a final note of this topic, we also discuss often catalysis, and already we gave an example of catalysis, which is heterogeneous catalysis, when we discuss the Langmuir adsorption isotherm, but we did not discuss catalysis as such. Now catalysis means actually, so if I have, suppose A is going to B and we have some kind of activation energy, so the rate is dependent on this particular activation energy. Now this, if this is for the energetics for an uncatalyzed reaction, for a catalyzed reaction the rate of the reaction will be faster. The reason is the catalyst actually provides an alternative route. It actually binds to the substrate and then again gets regenerated. So that's why it is catalyst. It doesn't stoichiometrically take part in the reaction, but in effect it actually reduces the activation energy. And as you know, the rate constant is proportional to exponential minus activation energy by RT. In a result, what happens, reduction of activation energy increases the rate of the reaction. So the reaction is said to be catalyzed. The rate actually increases. There are many examples. We usually divide the catalysis into two parts. One is heterogeneous catalysis, where the catalyst and the reaction are in different phases. Like for example, there are many gas phase reactions. The most notable is the catalysis for production of ammonia, which is known as Haber process, where actually we use iron catalyst. And you know that these iron nanoparticles, these are solids, whether these species, nitrogen, hydrogen and ammonia, they are all gaseous species. So it occurs on a surface where I have first nitrogen, it gets adsorbed to the surface, and then hydrogen gets adsorbed, and then they react, the absorbed species react between them, and then the ammonia comes out. So this is called as heterogeneous catalysis, because this is a solid and this is a reaction between solid and a gas. Similarly, you can think of a same phase catalysis, which is known as homogeneous reaction, homogeneous catalysis. Examples are acid base catalysis. For example, you can have any ester, RCOO, say R prime, and then water can actually hydrolyze this ester bond, and you can get the acid and the alcohol back, which is nothing but the addition of a water, but this is catalyzed either by H plus ion, or basically any acid, or by an OH minus or an base. So these are the examples of homogeneous catalysis. So catalysis is defined as heterogeneous or homogeneous catalysis. One very important example for under homogeneous catalysis is enzyme catalysis, where actually the enzyme bonds to a substrate to give you the enzyme substrate complex, and this enzyme substrate complex eventually gives you the product plus the free enzyme back. So the enzyme is a catalyst, it doesn't take part in the stoichiometry. The overall stoichiometry is the substrate going to the product. Now as you see, if you follow carefully, this is nothing but the way I have written it. The entire reaction substrate going to product catalyzed by enzyme is using two steps which we just discussed. In the first step, the enzyme binds with the substrate to gives you the enzyme substrate complex, and in the second step the enzyme substrate complex gives you the product. And then you can actually use the steady state approximation for the intermediate, and in this case the intermediate is the enzyme substrate complex. And then you get a very beautiful discussion based on the work by Michaelis and Menten, and you talk about Michaelis-Menten kinetics. We will not cover Michaelis-Menten kinetics in this course because it is well covered in the textbook. So Michaelis-Menten kinetics for enzyme catalysis. So you can always go back and have a look how it looks like, and then so if I usually it is plotted as the initial substrate concentration versus the initial velocity, and then something like this V0 and initial substrate concentration, and then you see that it actually reaches to a maximum speed which we call as V max. So all this discussion you will get it in any standard textbook. And then people talk about the alternate representation of the Michaelis-Menten kinetics, which is known as the Lineweaver-Burk plot. So which instead of V0 and S0, there you plot actually 1 over the reciprocals, 1 over V0 and 1 over S0, and then you get a linear plot, and these plots are known as Lineweaver-Burk plot. And these plots are very, very interesting when you discuss enzyme inhibition, because there you show how basically the enzyme inhibition is a competitive or non-competitive one, in the sense that the enzyme and the inhibitor and the substrate are competing for the same site of the enzyme, or they are competing for two different sites of the enzymes. So those things are also covered in the YouTube lectures of this preceding course. Now what we have done so far, we have given you an overview of how basically this the overview of the introduction to chemical kinetics, what are the rate laws, what is the definition, and how one can think about the integration of the rate laws, and then what are the specific type of reactions like equilibrium, opposing, and consecutive, and then how a multi-step reaction or a composite reaction can be decomposed into many single step reactions, so that we can actually explain the observed rate law by doing all these maths. But we need some approximations, and often we use there are two approximations. So one is known as equilibrium approximation or rate determining state approximation, and the other one is known as steady state approximation, and these two approximations are equivalent if you imply or if you just apply certain conditions. And then we talked about little bit about the enzyme catalysis. There also you use the steady state approximation to get the final rate for the product formation. And now we'll discuss the more advanced topics on chemical kinetics, how one can actually think about reactions where actually the product significantly alters the rate of the reaction. So these are known as basically feedback reactions or the oscillatory reactions, but the product gives a positive or negative feedback to the reaction. We also talk about the other methods of solving the coupled differential equation for these particular cases. Before that, we'll give you a brief overview of how the kinetics all these experimentally determined things are arrive at this rate law, which means actually how you do the experiment. So we'll give you an overview about the kinetics measurement first, how one can determine experimentally the rate law for a composite reaction.